Hi everyone, my name is Dr. Naga Malleswari, Assistant Professor, Department of Mathematics from VJEC Institute of Engineering and Technology, Hyderabad. Today I am here to discuss about applications of derivatives. In that topic is maximum and minimum values of the function. In many situations we are interested in finding best or extreme values or highest or lowest values. Look at the picture. 3 examples are there. One is mountains, second one is ball, and third one is roller coaster. Here, mountains and valleys are there. Peaks are maximum and valleys are minimum. And in second example is ball. When the ball bounces, it reaches high at time to time. So the highest bounce is maximum and the ground level it reaches is minimum. Next, third example is roller coaster. In roller coaster, tops are maximum and dips are minimum. Let us see how these ideas appear in mathematical graphs. Here is the graph. In this graph, 2 points are there. One is local maximum, local minimum, global maximum and global minimum. Local means maxima or minima of a function in small region, whereas global means maximum or minimum of a function on the entire graph. Let us start with the definition of maximum and minimum. So that is global maximum and global minimum. A function is said to have global maximum at a point if its value is greater than or equal to other values. Similarly, a function is said to have global minimum at a point if its value is less than or equal to other values in the interval. See here, 2 figures are there. One shows the global maximum and the second figure shows the global minimum. So global maximum means here in global maximum, the function f of x has highest point at x is equal to c. The highest point on the entire graph which represents the global maximum, and in second graph at the point x is equal to c, it has global minimum. So that means on the entire graph at x is equal to c is the least value, so that it represents the global minimum. Next, coming to the definition of relative maximum and relative minimum. So another name of relative maximum is local maximum. A function is said to have relative maximum or local maximum at the point if its values is greater than or equal to nearby values. Similarly, if the function is said to have relative maximum or local maximum at the point if its value is less than or equal to nearby values. Global maximum and global minimum together form the global extreme values. Similar to relative maximum and relative minimum, the relative maximum and relative minimum together form relative local extreme values. Let us see the example problem for better understanding of the topic. The profit function p of x of a company selling x items per day is given by p of x is equal to 150 minus x into x minus 1600. Here profit function p of x is equal to 150 minus 1600 is given, that is cost. Find the number of items that the company should sell to get maximum profit. Also find the maximum profit. So first what we have to take here, the profit function p of x. P of x is equal to 150 minus x into x minus 1600, which we call it as a equation 1. So to find maximum or minimum, first we have to differentiate it with respect to x and equating it to 0. We get 150 minus x, here we are applying u into v rule, then we get 150 minus x into 1 plus x into minus 1, which is equal to 0. Then on simplification, we get x is equal to 75. 150 minus x minus x which is equal to 0, 150 minus 2x is equal to 0, then x value which is equal to 75. X is number of items. So number of items either it is produced or sold. Next, again differentiate it partially with respect to x, we get minus 2. So second order partial derivative at the point x is equal to 75 is less than 0 because we get negative value here, it is less than 0. Therefore, the profit function p of x is maximum for x is equal to 75. So that means the company should sell 75 items a day to make the maximum profit, and the maximum profit will be, to get the maximum profit we have to substitute or we have to use x value in the given profit function, then we get p of 75 which is equal to 4025 is the maximum profit. Next, previously we discussed maxima and minima of single variable. Now we are discussing maxima and minima of two variables. Let f be a function of two variables. Previously we are taking only one variable, now we are taking two variables, that is x and y. A function is said to have maximum or minimum at the point if its value is greater than or less than or equal to nearby values. If f it is either a maximum or a minimum value, then the function at the point a comma b is said to have an extreme value. See the necessary conditions. So to get the maximum and minimum, here are necessary conditions are there. A condition is necessary. The function f of x comma y is said to have maximum or minimum at the point a comma b. Then first order partial derivative of f with respect to x at the point a comma b is 0, and first order partial derivative of f with respect to y at the point a comma b is equal to 0. So that means first order partial derivatives with respect to x and y must be 0 at the point. Next, here important point that we have to remember, that is stationary value. Function at the point a comma b is said to have the stationary value. First order partial derivatives with respect to x and y must be 0 at that point. Next, sufficient conditions to find out the maximum and minimum of functions of two variables. So first order partial derivatives which is equal to 0 at the point a comma b. Now we have to find out second order partial derivatives also at the point. Here we are giving some notations L, M and N. Second order partial derivative of f with respect to x at the point a comma b, it is also denoted by fxx and it is denoted by the notation L. Similarly, second order partial derivative of f with respect to x and then with respect to y at the point a comma b is denoted by m. Finally, second order partial derivative of f with respect to y at the point a comma b is denoted by n. So that here we are taking three notations, that is L, M and N. Next, here are some rules that we have to apply to get the maximum and minimum. Ln minus m square is greater than 0 and L value is less than 0, then the function at the point a comma b has a maximum value. If ln minus m square is greater than 0 and L value is greater than 0, the function a comma b has minimum value. If ln minus m square is less than 0, here saddle point is existing. So saddle point means neither maximum nor minimum is existing here. And last, ln minus m square is equal to 0. So that means the test fails to provide a conclusion and the point needs further investigation. Look at these examples. Manufacturing and packing. This is classical box problem. Calculus is used in manufacturing and packing. So that means for material efficiency and cost saving, we are using calculus. Here two panels are there. In first panel, inefficient design is there, and in second panel, optimized design is there. So inefficient design means wastage is high, whereas in optimized design, wastage is minimum. In inefficient design, here maximum volume, higher production cost, finally it results high surface area per volume. Whereas in optimized design, wastage is minimum, minimizing the surface area, production cost, which gives the profit maximization, and finally it results optimized for the maximum value. So in this classical box problem, where the manufacturer determine the dimension that provides the maximum volume for a package using a maximum surface area of the material. So that means it reduces the waste and lower production cost. See the example for better understanding. A rectangular box open at the top is said to have 32 cubic feet. Find the dimension of the box requiring least material for its construction. So least material for its construction means we have to find out the maximum material that it is required for its construction. See here, the rectangular box top is open. Minimizing the material for the box, here we have to find out. So to find out the minimizing material for the box, first we have to define the variables and objective function. For this we have to take volume of a rectangular box, V is equal to XYZ, and surface area S is equal to XY plus 2XZ plus 2YX, because one side is open top box is there. So that here we are taking S is equal to XY plus 2XZ plus 2YZ. Next, in second case, we have to reduce two variables. So that means in place of Z, we have to substitute V by XY. Then we are reducing it to two variables. And in third case, we have to find out the critical point. Finally, we have to solve it for optimal dimensions. Define the variables and equation. Let X be the length, Y be the width, and Z be the height of the rectangular box. Volume of a rectangular box, V is equal to X into Y into Z. So that means length into width into height. Volume which is already in the data, we have to take V is equal to 32. Surface area for the open top box, S is equal to XY plus 2XZ plus 2YZ, because one base and four sides are there in this box. Next, express surface area in two variables. From the volume equation, we get Z is equal to 32 by XY. From this equation, we get V is equal to XYZ, which is equal to 32. Then from this equation, we get Z is equal to 32 by XY. Next, substitute Z into the surface equation. We get S is equal to XY plus 2x into, in place of Z, we are taking 32 by XY plus 2y into, again in place of Z, we are taking 32 by XY. We get XY plus 64 by Y plus 64 by X. Next, we have to minimize the function in third point or in third step. Find the partial derivatives. We have to find out the first order partial derivatives and equating it to 0. Here first order partial derivatives are y minus 64 by x square, and equating it to 0, we get the value of y, and the value of y here is 64 by x square. Similarly, differentiate it partially with respect to y. From this we get the value of x. X is equal to 64 by y square. Substituting y into the equation for x, then we get x is equal to 4. Next, last step here is solving for all dimensions. So we already find out one value, that is x is equal to 4. Using that, we have to find out remaining two values, y and z values. Using x is equal to 4, we get y is equal to 64 by 4 square, that is 4. Similarly, using x is equal to 4, we get the height z value, that is 2. Therefore, the dimension of the box that require the least material for its construction are 4, that is length, 4 for width, and 2 feet for height. Next, look at some examples. Communication system. In communication system also we are using calculus, and here calculus is used for advanced network optimization. Here two panels are there. One is signal to noise ratio. Second panel is cell tower placement. Signal to noise ratio, it is maximization of data transition, whereas in panel 2 cell tower replacement, here it is minimal geographic coverage of area. Here in maximization, maximize data transmission clarity. So maximizing the data transmission clarity means it is taking more time and data clarity is less, whereas and it ensures robust data link. So that finally here we get maximum signal to noise ratio, whereas in cell tower placement we have to optimize the signal strength and the maximum signal to noise ratio to ensure the clear data transmission, so that the placement of cell tower is often determined by finding the minimum number of towers needed to provide maximum geographic coverage. If suppose inefficient placement is there, so that it gives large gaps and high inference, so that here we have to take minimum towers for maximum coverage. Calculus is also used in robotics and kinematics. So in robotics, it explains path planning. Optimization is very crucial in robotics for path planning. To calculate the minimum energy path or the maximum time required for the robotic arm to move from one point to another point. By finding the minima of a power consumption function, robots can operate more efficiency and extended battery life. In business and economics also we are using calculus. In business, calculus is used for optimization. So companies use maxima and minima to find the sweet spot for profitability. So that means profit maximization and cost minimization. By analyzing the profit function, so here profit function means P of x, which is revenue minus cost. Profit function, business determine the exact production level that yields the highest return. And in cost minimization, calculus helps in inventory management to find out the minimum cost for shipping and storage while meeting the consumer demand. So another application here is calculus in structural engineering. Calculus is used in structural engineering, in construction. It is used to determine maximum load. A beam can support or the maximum amount of material is needed to maintain the structural integrity. See here in structural engineering, here load is there. Here first we have to model the beam, and calculus is used in bending moment of the beams. It is used in stress analysis. And also we have to find the point of maximum stress. Point of maximum stress here 3 points are given with red dots. So main stress is here in these 3 points. Then optimizing the material use. And finally, stress is distributed. Stress distribution is clearly shown in 6th point here. Here, red shows the stress distribution region. If the color is blue, here stress is low. Whereas here the color is red, that means here the stress point is more. So for example, if we design an arc or the bridge, so engineers calculate the point of maximum stress to ensure the material and used can withstand the pressure. So these are the simple examples where calculus is using. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.